Okay, guys, what up? Here we go. Test review, work, power, energy. All right, so we're going to get some basic things in here. First one, in physics, work is defined as what? Would anyone like to give an answer? How about you over there? What do you think? It's literally highlighted.
Force times distance.
Force times distance. Ba-bam. I don't want to do that necessarily because I'm recording, so I don't want to use names. That's why.
So you just said you were.
That's why. I mean, yeah, that's why I did. So, can someone give me the answer for number 2? What is the unit for work? Yes.
C.
C, the joule. You're not wrong. Ba-bam. All right. What about the next one? Anyone have a chance or an idea for what the next one should be? Well, here's the triangle for it right here. So if P is power, if I cover that up, it's work
Divided by time.
So which one of those makes the most sense? You're right. C. Good. What is the unit for power? What? What? No, it's watt. But you should know that. Okay. Yeah. Unit for force. Well, we should always know what that is. I'm not going to highlight that one. You guys should be able to complete that. Number 6. To determine the work done by dragging a box across the floor if you push with 235 newtons and the box moves 21 meters. So I have a force and I have a distance this thing moves. Work, W, is equal to force times distance. So you're going to multiply those two things together, and that is going to kick out an answer here of this 4,935. Okay. And what did I do to get those? I multiplied 235 times 21. Now, what about 7? How much power are you going to generate dragging the box from problem 6 in 15 seconds? Okay, so what do they want? Power. Covering P up in the triangle, it's W divided by time. So the work that you did was the answer for number 6. So they said, okay, how much power do you generate by dragging the box from problem number 6? All right, doing all that work in 15 seconds. So you're going to take 4,935 joules, divide that by 15 seconds, and that's going to kick out, bam, 329 watts. And the next one, a person weighing 600 newtons gets on an elevator. Now the elevator lifts this person 6 meters. All right, so it's lifting them in what direction? All right, the elevator is lifting them up, and what direction does it move? It moves up. So remember, work needs to be done in the same direction. All right, the force and displacement need to be in the same direction. If force and displacement are in opposite directions, technically negative work would be done. So they want to know, okay, how much work or how much power is being used here? So you have your force being used, you have the distance, and you have the time. So work is force times distance. So you can do it one of two ways. Work equals force times distance. Do that first. Hit equals. That will be W, and then divide by time. Or power can equal, right? If you replace F times D for W, it would be force times distance divided by time. So you're going to do 600 times 6 divided by 10. And you're going to be left with 360 watts. Now, in number 9, an object that has kinetic energy must be doing what? You guys should be able to know that one. What would that be? Kinetic has to be doing what? Moving. Good. All right. Number 10, energy change from one form to another with no net loss or gain. Is that sometimes true, always false?
Sometimes true.
Always true. Energy cannot be created nor destroyed. So it's always going to be around, just changing from one form to another. I'll come back to that. Sorry about that. I literally thought I had it. All right, number 11, you guys should be able to absolutely do. That was on. We did that a few different times last week. Number 12. What about number 12, Doe? Yeah, 12, Doe. Potential energy is the energy of an object because of what? The energy an object has because of what?
Either speed or density.
Either speed or density.
Or size.
Or size. Wow, that's actually incredible. You picked all of the not right answers. Actually, I'm not even mad. That's amazing. Density, no, we haven't talked about density. Density, we haven't really even talked about.
So, height and location.
Yeah, it's height and location. Speed is needed for kinetic energy. And size. So size, right? You could have like a beach ball filled with air and like a basketball, right? The beach ball should be bigger, has more size, but which one has more mass? The basketball. So that's going to come into play usually a lot more in physics. Well, but if you hold the two up, you would be able to feel the difference. And so potential energy has to deal with the height and location. Remember the idea if I dropped like a lacrosse ball on your head from 3 inches up versus 3 feet up, which one's going to hurt more? The one that was 3 feet up. Why? Because when we gave it more potential energy, it has more energy to convert into kinetic by the time it hits your head, and therefore it's going to wind up hurting you a little bit more. All right, so you got that, dude. Now, 13, what are we going to do here? They want us to calculate the what? The potential energy, the PE. The PE, what is the equation for PE? Anyone remember? It's got 3 variables. M, G, K. No, I'm just kidding. MGK he's like a, I don't know what he is anymore. He's a rapper / like rock person, whatever. But it's mass times gravity times height. So PE is equal to mgh. That is for gravitational potential energy. Okay, well wait, yo, Mr. Lombardo, I only see 2 numbers in here. So WTF, what's the force? Watch yourself. So I only have 2 numbers, so what do I do? Well, this is something that you're going to need to know, right? So you have the answer is going to be 1,250 joules, and how? Potential energy is mgh. So you're doing 50 times 10 because gravity is 10. Even though it's not given in the problem, even though the number 10 is not written in the problem, it is your responsibility to know that gravity, all right, is going to be 10.
How did you just do that?
Don't worry about it. So I have M, here's my mass. G I have to know is 10, and it's not given in the problem, but if I know what the equation is, G, all right, ba-bam, and then times that by the height of 250. So we should have a final answer here of 1,250 joules. Joules. Work and energy are both measured in joules. Love it. It's the best. Don't be hating. It doesn't taste like black, honestly. If you took a sip of that, you'd be like, this one's not bitter. Like, it's got some like, it's like a little pre-flavor to it, that's all. I mean, it doesn't smell as good as it did when I first brewed it, but sheesh. Take a whiff of that.
Oh, actually, that's not bad.
Right? So it's like kind of like pre-flavored, and the flavor is caramel vanilla.
What does that say?
50 times 10 times 2.5 equals 1,250 joules Bam. Honestly, I'm surprised no one else has said it. What do you notice about the computers?
They're new.
They're that new. That's that new. That new. So please, for the love of God, take care of it.
What is the last number?
I will go find the worst possible Chromebook for you to use if you do that. Huh?
What's the last number? 2.5?
Yeah, 1,250 joules.
My eyes are getting worse and worse.
I mean, you can move up. You can sit behind Dom if you want.
No, I'll stay 6 feet, sir.
Not when everything comes back to now. Not when we all go to the 4 or 5 days, whatever the hell it is.
Yeah, but that's gonna be like next week. Everyone starts going.
I think May 10th is when juniors do that for us.
What?
But that's if everything goes smooth. There's no any outbreaks. Yada yada yada. All right.
You're gonna send us all back. Someone's gonna get COVID.
Yeah. Well, hey. All right. I like this one. Ready? How much work is being done by holding a 15 Newton basket right at the food store while waiting in line
Of course it's food.
for shut up. While waiting in line at the grocery store for a time of 180 seconds.
0 joules. I like this one.
2,700 joules, 0 joules. C, you've gone too far. D, bruh, it's B.
It's big. Yo,
This
what?
was like an old test that I had given, and I had kids actually like put D down as an answer.
I mean, they're not wrong. It
Yes,
is
they
B.
are.
It is B, bro. Like,
Bro,
it's
the
zero.
answer is B. So you write B, not D. They were trying to be like little smart asses about it, and guess what? Nope,
You're the
ain't
one-
working.
You're the one being smart.
No. I'm literally trying to give you an answer, and then you're like, oh, let me try and be funny about it. Well, too bad. Wrong. You're wrong. Okay, so a pendulum. A pendulum swings back and forth. So think about a grandfather clock, all right? Or literally like a yo-yo that's fully got the string fully let go, and you're holding it by the very top part of the string, and you rock it to a certain height, and then let it go. It's going to go back and forth and back and forth. So what they wanted to know, which one of these is correct regarding its energies. So the endpoints of the swing, its energy is all potential.
You have one of those things that go like
Something I can make a makeshift one, but I don't have like a one straight up right here
that.
with me.
Those are so
Look,
satisfying.
use that.
No, I don't want to use that.
Why not?
We don't want to touch that. Anyway, so the idea with that is, here's a picture of a pendulum. Actually, you know what? We can simply
Isn't it
just
the
do
metal
this.
ball thing that just goes-
Huh?
It's the thing that goes with the metal ball.
Yeah.
Yeah. Those things are
Right? Yeah, like
sick.
a little quick video. Oh, well, I don't want that one. I don't want that. Okay, that's
It's a
annoying.
minute one.
So, here you go. It rocks back and forth. It rocks back and forth.
Dude, doesn't it go on forever?
It would go forever if it were in a vacuum and there was no air friction to slow it down. So with this being said, if I were to kind of just taking a look at this, right, it rocks back and forth. So it goes to its two endpoints. Now, what would you tell me is going on about at the two endpoints? What can you tell me, or what would you tell me about the speed?
It's getting faster.
So if it, let me see if I can make this. What the? Really?
Just press control pause. Or copy it on that. Oh, look at that, genius.
All right. So you have the bob or whatever, the ball, and it rocks back and forth. So originally it's at this position, yeah? So from this position, this would be where the height of the thing is 0. Now, if I rock it back up to this point here,
Pause
okay, now I gave it what? Height, right? Now, if I'm holding it still, it's not moving, so there's no kinetic energy. Now, if I let it go, what happens? Gravity's going to push it down, causing it to lose height and gain speed. Now, it gains speed. As it gets to this point, it's going to be the fastest that it ever is. And now it's starting to slightly go up against gravity. So it's losing speed. And when it gets here, At this one instant in time, it has 0 speed, and then does what? Changes direction. Good. And then it's going to come back. All right. So then it's going to gain speed. Its fastest right here. Lose some speed, but it's at that point it's gaining height, so it's gaining potential energy. Now, if it were in a frictionless environment like a vacuum, this thing could rock back and forth for the whole time. So then going with this, pendulum swings back and forth. Which statement is correct? At the endpoints of its string, its energy is all potential. Just thinking no?
How can it be all potential?
Well, how could it be all potential? It could be all potential because at the very, very endpoints, at that instant, what is the speed?
0.
So there's no kinetic energy there. So yeah, it's got to be potential. So that's good. That's correct. What about this? Potential energy is transforming to kinetic energy and back.
I mean, it is.
Right? So when we had this thing chilling by itself, we rocked it back up. What did we give it? We gave it potential. We gave it height. We gave it potential. And then we let go. What happened? Then it's starting to pick up, gain speed, which means it's going to have kinetic energy. And as it loses some potential, it gains kinetic, and now it's starting to slow down. So it's losing some kinetic energy, but it's gaining height. So then it's gaining potential. So it is transforming back and forth between those two. The lowest part of the swing would be all kinetic. So once you bring this up, rock it, and let go, if this was the original starting position, we would say the height is 0. Now, if we rock it back and let go, when the height is 0, it's going to be going the fastest. So at the lowest point right there, it would be moving the fastest. It would be all kinetic energy. So yeah, we got all of the above. Word. All right, bet. Roller coasters, beautiful thing for mechanical energy. Mechanical energy, ME. We went over this last week. Mechanical energy, ME, is...
It's A. It's just on the
Is it though?
Yes.
Well, it depends on what they're asking. I like what you're saying. You're thinking it's A right off rip. But you have to read the question super carefully. So before we say that, mechanical energy is the sum of both kinetic and potential. Now, if we know what it is at any one point, it has to be the same throughout the entire thing because we're neglecting friction or anything like that. So here,
17 is...
well, hold on. Don't jump the gun for me. Which point is the highest? A. So at point A, you would have the most potential because M times G times H. If the mass doesn't change, gravity's not changing, the only thing that can change is the height. So the most potential energy you're going to have is at point A. And then E, and then B, then D, then C. But they're asking us from the least amount of potential to the most amount. So it would be C, D, B, so CD Bay. CD Bay? CD Bay? B Bay? Whatever. Yes. So now, kinetic energy. So kinetic energy, greatest kinetic energy is going to be essentially on a roller coaster problem like this, is going to be the opposite. So at the very, very highest point of the track, usually what do they do when you get up there? I'm not a fan of roller coasters either. I wish I loved them because I'm a physics teacher and there's like awesome, cool physics stuff behind it. So do I. I hate the feeling and I don't like heights. So
heights and speed is fine, but roller coasters
It's just
like
that pit, that stomach, and that feeling in your stomach, I hate
I
it.
feel like when I first time I went on one, I felt like I was gonna die. So I just never did it.
Wasn't a fan. Not a fan. So, but with this, at the very, very top of roller coaster, even though you may not go on them all the time, what do they usually do right at the top?
They stop.
They stop first, right? They stop first, and then they go. So guess what? At the very, very top, we pretty much are, for the most part, all potential energy. And now we start to rock, and now it starts to go. Now what are we doing? What happens to our height? Go down. So if height decreases, what happens to potential energy? It decreases. Now, as it's going down, what happens to the speed? It's starting to, and that means kinetic energy is going to increase. So where's the height 0? At which point?
No, C.
C. So since C right there is at the lowest, think about it. It's gaining speed, gaining speed, gaining speed, gaining speed, gaining speed. C would be where it's at the fastest. So that is where it would have the most kinetic energy. So essentially, it's like the opposite. If you know how most potential to least is based on height, kinetic energy would be the flipped for most. So the lowest height is C, the most kinetic energy would be at point C. Now they want us to go from greatest to least, so this one should be C, D, B, E, A. It's actually going to be the same piece here.
Isn't A the greatest now?
Well, A has the greatest potential energy, but this problem asks kinetic. So remember what we said we just said it at point A. What do the coasters usually do right at the top?
Stop.
They stop, and if they're stopped,
Oh,
you can't have kinetic. Total mechanical energy is found by the sum. All right, you add in kinetic energy and potential energy at any point. Number 19, you should be able to do this no problemo.
so if there's a loop,
Wait, what was each thing?
what would that be? Would that be
If there's a
slowing
loop,
down?
so the loop.
Because you're going up,
So yeah, think about it, right? Anytime, if there's a loop, what happens to the speed?
it slows down.
It's going to lose some speed because why? What is it gaining?
You're going up.
You're gaining height. So it means you're gaining potential energy.
And then you're going straight, kind of.
What's the biggest roller coaster you ever been on?
Then you're going straight, right? And then back down.
The highest roller coaster I've ever been, it was somewhere in Hershey Park. I went one year for like a chaperone of a field trip.
Along with the kids.
Yeah, right, we went with like a bunch of seniors and like my cousin was there. It was like had to be like 3-4 years ago. And like I didn't really necessarily want to go on, but like
The kids
the kids were all like, yo, they're not making fun of me. They're like, yo, Lombardi, let's go. You gotta jump on this. So I was like, God, all right, fine. I went on like 3 of like the bigger guys, and then there was like a 4th one that I was like going to go on, but it was like starting to get like cloudy and rainy. And they like by the time like the group I was with, like most of the chaperones, by the time we got up there, like they couldn't go on it because it was like raining and they shut it down. So I was like, haha, suckers.
Hell no.
I didn't like that because it like started like up high and the first drop like caves in a little bit. I was like, I didn't like
The
that.
one at Seaside is crazy.
At least you
come
did
out.
like.
They scary.
At least you did like 3.
Yeah.
I went on one roller coaster in my life. Never been on one ever again.
I'm like, okay, cool. I was happy I went on it because it was like, something like I hadn't done in a long, long time. But like,
King of the Cop.
like King of the Cop, I would freak out because I'm scared of heights, and you're going up like you're looking basically straight up, and then you just like they pause you at the top for a second, and then you're looking down and stuff, and then it's like, okay, you're going to experience a lot of G-force coming on the way down. What is G-force? It's basically your body's accelerating multiple times of gravity, so you're feeling like you're getting compressed to that stomach. So when like fighter jet fighters, pilots, they do certain maneuvers when they accelerate too much, right? So you can accelerate by speeding up, slowing down, or changing direction. So when like they do certain crazy dives and maneuvers, they may not necessarily be changing speed, but they're changing their direction at a high speed so fast that they experience 4, 5, 6, 7 Gs, which is basically like 7 times your own body weight, like compressing you like on all sides. And they wear special suits to try and help them, but they also have to do certain training to try and like, because a normal human being, if they went through that, like you'll see like sometimes they take interviewer people up and like they'll lose consciousness for a second. Like you don't want to do that when you're driving like a $2 billion fighter pilot or like a jet plane.
You ever been to the air show before? That shit's crazy.
Yeah, the air shows are awesome. They are
I
cool.
don't even think I'd go on King of the Cop for $1 million.
I would 100% go on King of the Cop for $1 million. But
Hell no.
I wouldn't even go on the one at Seaside, and that's
the ones at Seaside scare me more because like they ain't as professional. All right, so this one, guys, there is no friction. So what they want you to do is list them from the lowest kinetic energy to the highest kinetic energy. Okay? So again, that one is going to be ranked based off of what?
Let's see.
Which one do you think has the lowest kinetic energy?
Either 3 or 6.
Either-
I'm gonna go with 6.
That would be the lower potential.
7, 3. 2.
1. Think about it. Right at the start, you have the most potential and least kinetic because you're really not moving. Now you're starting to accelerate. So you have the highest height here out of the six parts of this that are shown. So you're going to have the least amount of velocity here, so the least amount of kinetic energy. So remember, it's like the opposite of potential. If I said, hey, rank them from most to least potential. 1 has the most, then 5, then 2, then 3, then 6. So kinetic energy would be like the opposite. The most kinetic energy would be 6, then 3, then 2, 4, 5, 1.
It's definitely not being one.
All right, so but they wanted now, but since they wanted the lowest kinetic energy, 1 would be the lowest. Then 5, 4, 2, 3, 6. So you're looking at probably at C. Okay, 20. You guys should be able to figure this out. According to the scientific definition of work, pushing on a rock accomplishes no work unless there is a. You can apply a force, right? I could push on that wall. Am I doing any work?
Wait, which one?
20.
Oh. And apply force greater than the speed.
Possibly. An applied force greater than its weight.
It's either A or D.
It's either A or D. Okay, good. Remember the first video that we watched, right? If I lift something and I apply a force greater than its weight, yeah, in order to like hold it up. So like the groceries. But if I'm just walking, what's going on? What am I doing work if I'm holding the groceries at my sides? No, because the displacement of the object isn't in the same direction. So the movement of the object needs to be in the same direction as the force.
So D.
Yes, letter D. Letter D. Okay, you should be able to figure that one out. You should be able to figure out 22. What about 23? What is the law of conservation of energy? What does it state? It states that energy cannot be what?
Use faster than it's created.
Well, what was the definition that we used last week? Energy cannot be created or destroyed. Okay, so if you know that that is the definition, which one of those is like the closest thing to that? And now you originally said which one? You originally said D, right?
Yeah.
Energy cannot be used faster than it's created. Well, guess what? Remember? Energy cannot be created, so that definitely can't be an answer. Energy must be conserved, and you are breaking a law if you waste energy. You're not necessarily breaking a law. Yes, good job. The answer would be C, right? So the supply of energy is limited, so we must conserve. No. The total amount of energy is constant. Yes, so it is because it can only change form. So energy cannot be created nor destroyed. It can only change form from one to another, like potential to kinetic, or if you drop a tennis ball, right? It has potential as it's falling. It has kinetic. When it hits the ground, there's sound. It loses some energy due to sound, heat from the impact, and friction. So there's a bunch of different things going on there. So C would be our guy. C would be our guy for 23. I didn't answer a couple, but those ones you should definitely be able to answer on your own. Now we have, down here, we have some equations. Kinetic energy, 1/2 mv squared. Mechanical energy is the sum of potential plus kinetic. And potential energy is mass times gravity times height. And if you wanted to find height, it would be potential energy divided by mass times gravity. And the underlying thing, you tell me whether or not it's going to be kinetic or potential energy. You can just use Ke or Pe. So if you serve a volleyball and it's got a mass of 1.7 kilograms, the ball leaves your hand with a certain speed. What kind of energy are we looking at?
Kinetic.
Kinetic energy, Ke. Now you got to calculate it. Oh, crap. Bugger. Okay, so now we got to calculate it. So kinetic energy is equal to 1/2. What's the mass? 1.7 times, what was the velocity or speed? 20. And remember, only the velocity gets squared. Only the velocity gets squared. And how do I do the square thing again? Control period. Good. So then you're going to type this into your calculator. 20 squared times 1.7 divided by 2. You're going to get an answer of 340 joules. 340 joules. Number 2, you got a baby carriage sitting on top of a hill. The hill is 23 meters high. The carriage plus the baby have a mass of 29 kilograms. Still seems like rather a lot. And so the carriage has what kind of energy? What kind of energy are we thinking? Potential. If it's just sitting, right? If it's just sitting. So how do we do that? Potential energy is equal to mgh. So what do I do? Wait a minute. Mr. Lombardo is only 2 numbers. What do I do? Well, identify again. What are the variables? Mass is m. What is lowercase g? Is what do we? It's gravity, right? So in gravity, that's the thing you have to know. It's 10, even though it's not in the problem. All right, it's not labeled as a number in the problem. That is something you must know. So we have the mass, which was 29, times gravity, which is 10, times the height, which was 23. So 29 times 10 times 23, 6,670 joules. All right, and I'm just going to write this in there as well. G is not given in the problem. But you must know that it stands for gravity and its value is 10 meters per second squared. All right, so even though G is not necessarily given as a value in the problem, when you are using MGH, you're probably only going to be given 2 numbers. That is something you must remember and recognize. G is not given in the problem. So you must know that it stands for gravity and that its value is going to be 10 meters per second squared. That's what we use, okay? Other classes or other whatever, they may use 9.8, but we're using 10 because it just makes the calculations a little bit cleaner, a little bit easier. All right, so basically, guys, if it has speed in there, it's going to have some kinetic energy. Okay, that's fine. All right, now we're going to look at these ones here. So these are conservation of energy problems. So conservation of energy means essentially energy is not going to be created nor destroyed. It's going to be transferred from one form to another. So mechanical energy. Mechanical energy is not written in here. Let me do this real quick. Mechanical energy is equal to what? Potential plus kinetic. So once you find your mechanical energy at one point, it needs to be the same at all the other points for that problem, for that situation. So let's take a look at 23 and just, follow me here. At the very, very top, what does it say our potential energy is? So, right? Oh, crap. Oh, geez Louise, what'd I do? Can I do the pointer? No. What is this? Pointer focus? Fireworks. I don't know what the hell that is. Flashlight. I don't like flashlight. What the French toast? All right. Anyway.
Spotlight,
Yeah, we got a little spotlight. So what is the potential energy at the very, very top here at the first thing? 0. I'm sorry, 30. Jesus.
God,
Yeah, the flashlight is throwing me off. All right. So the spotlight here, if you see that the potential energy at the top is 30, and that this little slope here and these steps are all equivalent height, and we're assuming it's the same ball. So what do you think the potential energy would be at all those top points? Good. That would make sense, right? It would make sense to be 30. So the potential energy for this first one here is going to be 30. That's the next thing that we could fill in. And then the next one we could possibly fill in is also, again, at the equivalent height. So it should also be, what the French toast? I hit shift by accident. Also be 30 joules. Okay, but now they're asking, hey, notice how many steps are there? 3. So if the potential energy right here at this top one was 30, and these steps look like they're equal, and the bottom, what is the height at the bottom?
0.
So what should the potential be there? 0. So what do you think it would be at these other 2 steps? So at this one, what do you think it's going to be?
30.
Well, if at the top is 30, now you're doing what with height? 20. 20 would make sense, yeah. Because you're going down, right? And then you're going down one more, and they look pretty much even. So it'd be like 30, 20, 10, and the bottom 0. Okay, well, wait a minute. What the heck's going on over here? What do they want from me there? What do they want going on right there for this kinetic?
Is that an 11?
No. This is just like little lines showing that it's like falling down. So it has kinetic energy. Now,
So it'd be 0?
can the kinetic energy be 0 right there?
I mean, it's
Potentially. So usually when it's drawn like this, all right, when it's drawn like this, or how it may be worded in a problem is, okay, what is the kinetic energy right as this thing is about to strike the ground, or right as it's touching the ground? That one instant where if the height is 0, all the mechanical energy that we had in that problem is now transferred to kinetic. So the kinetic here would be 30. It's easier seen in number 24. So let's take a look at 24. Right, so take a look, right? Mechanical energy is potential plus kinetic. Here.
I get it, bro.
So if we know that it's going to be, the mechanical energy is going to be the same at any single point, yeah? So we have 30 because it wasn't moving up here. Not moving yet, so it's 30. Right here, if the potential energy is 0, kinetic energy would have to have been 30 in order to make that true. So keep that in mind for 24. So at 24, potential is 15,000. Kinetic is how much? 0. So mechanical energy is equal to, right, PE plus KE. You don't have to write this down, but I'm just doing it. So that's 15,000 plus 0 equals 15,000 joules. So the mechanical energy needs to be 15,000 at every single one of those points. So, okay, if the guy starts to jump, his height is decreasing. He's losing some height, so his potential decreased. But what is he going to wind up doing? Increasing his speed. So he's going to gain kinetic. Well, how do I know what the value is going to be here? How do I know what this value is going to be? Well, if, like we said up here, once you find the mechanical energy at one point, it needs to be the same at all. So if I know the mechanical energy right off rip is 15,000, this potential plus another number has to equal 15,000, or just do 15,000 minus that 11,250. And that is going to give me 3,000, I think 750 joules. The next one, he's 7,500. Well, 15,000 minus 7,500 is also 7,500 joules. How would you find this dude here, this KE? The same way. You'd find it the same way. Well, the mechanical energy's got to be 15,000. So I do 15,000 minus that number, right? 15,000 minus that number, and it should equal what? 11,250 joules. Okay, and then Dom, right as he's about to land into the water, the potential energy is 0. So what should the kinetic energy be?
Wait.
What was the mechanical energy right off rip?
Oh, 15.
15,000. So that means the kinetic energy here would have to be 15,000.
I get it.
Yerp. And then this last one, potential energy. Look at the our pendulum here. Right at the first scene on the left side, we rocked it back. Potential energy is 10 joules. What is the kinetic energy? 0. So that means the mechanical energy needs to be what number? 10. So no matter what, at any one of these positions, that needs to be 10. So if potential energy here is 2, what is the kinetic energy got to be? It's got to be 8. It's got to be 8. Okay, what about this dude here? If the potential energy is 0, what would the kinetic energy have to be? In order to make sure that the mechanical energy is 10, kinetic energy would also have to be 10. Ba-bam. And then at the top, it looks like it's mirrored this outside position. So in this case, 10 joules for the potential. Excuse me, why is this being such a scotch? Go away.
Oh.